So last time we talked about the Diffie-Hellman problems, both the computational version and the decisional version, as well as talked about what groups are good. Not every group is good. Even our group generation algorithm needs to choose groups in a proper way, right? And we said there are two good choices. One is the prime order subgroups of ZP star, and the other was elliptic curve groups. I did not go into details about elliptic curve groups. It is in chapter 8, last part, but it is extremely complicated and I don't want to go through it right now. Okay, it's uh, it is an extremely fun subject, but if you're already struggling with groups, it will be hard. Okay, so since we are not going to use it again technically, I will leave that for now. Okay, I'll probably not cover it in this course. It's a proper number theory course, also algebraic geometry. So instead, we are going to start on chapter 9 and chapter 10. We are not going to go through it in full details. Um, chapter 9 basically tells you about how these algorithms work, and chapter 10 is going to finally introduce us to public key cryptography. Okay, so the last time we talked about two classes of cryptographic problems. we have discussed we have discussed two classes of cryptographic two classes of cryptographic assumptions. Okay, so there are two types of problems that we looked. First was factoring based, which was the factoring problem, the RSA algorithm, RSA assumptions, and that stuff. And the other was D-log based problems. D-log based, which was the D-log problem, the CDH, the computational Diffie-Hellman, and the DDH assumption. DDH assumptions. So, and we said that, oh, these problems can be done, as I said, in two classes of groups, into classes of groups, either the ZP star subgroups or elliptic curve groups. Okay, so I also talked that all these problems are hard, right? As in they have no polynomial time algorithms. But how hard are they? All these problems are believed to be hard. But i.e. have no polynomial time algorithms. Okay, but how hard are they concretely? Like, we would like to know, wait, how big a problem am I looking at? Okay, so this is just going to be a brief overview. These are just parameters giving you an idea. This is not really concrete, because cutting edge technology is like, there are papers and stuff which improve the bounds by margins of fractions, like reduce the power by -1/12, or by 100th, and these are still papers because these are significant improvements on the bounds. Here, I'm just giving you an idea of how big the bounds are. Okay? We saw that for recall, for symmetric key symmetric key algorithms, we said that block ciphers with n-bit key n-bit key are good. They're secure enough that they give security against 2 to the n time attacks. Security against 2 to the n time attacks. Okay, in case I didn't mention this before, it's not super important. This is not something that's going to come up again and again. So, hash functions, on the other hand, the way they were designed with n-bit output are secure against only a 2 to the n over 2 time attack. Right? This was the birthday problem that we saw. Factoring of a modulus of size 2 to the n. Factoring of a modulus of size 2 to the n, which is i.e. length n, using exhaustive search takes about 2 to the n over 2 time. Before square root of 2, you'll hit at least one factor, and so that is the square root time. Computing discrete logarithms, on the other hand, in a group of order 2 to the n takes about 2 to the n time. Okay, so this is using the straightforward algorithms, but are these really the best algorithms? Or are these the best algorithms? And the answer is no. There are much better things today. Okay. For example, the best known algorithm, factoring algorithm asymptotically, asymptotically, in a general number field, sieve, takes the time. Well, order of n is actually n if n is equal to n is of the size 2 to the n. Okay, if n is a 2 to the n bit, if it's an n bit number, then the symbol means n. Okay, so basically it's more or less saying log to the base 2 kind of. Okay. Running time heuristic is around 2 to the order of n to the 1/3 log to log of n, so log of n to the 2/3. Okay, and this is sub-exponential in n, because if you look at what it is, this is 2 to the order of, well, log of n is n to the 1/3 log. So this is log n to the 2/3, right? So it is still of the order of, it is still exponential 2 to the some exponent of n, right? But it is not full exponent. It is a power of exponent. It's 2 to the 1/3 of n. N to the 1/3, 2 to the n to the 1/3. So it's sub-exponential, so still not polynomial time. And this is like extremely huge, okay? Makes a huge difference in practice. Okay. Now, in real life, the exact constant term is also important. Exact constant term is also important, right? A constant term of 5 compared to a constant term of 200 is like, or let me say, a constant term of 5 compared to a constant term of 60, for example, is the difference between you downloading something in 5 minutes compared to downloading something in an hour, right? So it makes a huge difference. It doesn't feel like it. Okay, it's just a constant term. It's not going to change your negligible probabilities and stuff. But in real life, it does make a difference in running speed and everything. That's for factoring. What about so this is, I didn't say factoring. There's no algorithm for factoring somewhere for factoring. Okay. Similarly, the best known algorithm for D-log, okay, algorithms for D-log, algorithms for D-log, there are two types of algorithms here instead of just general algorithm. Two classes of algorithms. Well, one that works for arbitrary groups, one that works for arbitrary groups or generic groups. Okay, this is called a generic groups. And the other, which works for specific target groups. Okay. One that works for specific target groups. Now, what kind of groups? Well, recall that for some, recall that in some groups the problem is not even hard. Recall in some groups the problem is not even hard, right? So we only want to care about more hard groups, but even then, a special kind of group this works for. So what are the best generic algorithms? Best generic algorithm. Well, the best is still of the order of time 2 to the n over 2 in a group of order, in a group of order 2 to the n. So basically square root of n is the best you can do. And there's something slightly worse or good if for cryptography. It is known that this is the optimal for generic algorithms. This is known to be the optimal, for generic algorithms. So we still have made a lot of progress. The the naive algorithm, if you scroll up, was of the order of time 2 to the n for a group of size 2 to the n. So we have said that on a group of size n, we are now taking square root of n time. Okay? But you can show that you can't do much better than that. Okay? Now, the best known algorithm for subgroups of ZPN, best known algorithm, for subgroups of ZP star is the number sieve. Number field sieve. Number field sieve, which is, as mentioned above, runs in time, running time heuristic. Why is it heuristic? Depends on the implementation. But this is again running in time log 2/3 of p. Great. So you can do this pretty quickly, relatively. What about elliptic curves? For appropriately chosen elliptic curves, appropriately chosen elliptic curves, curve groups, there is nothing better than the generic algorithm. There is nothing better known. Nothing better than generic algorithms is known. Okay, and this is why there is a current movement, like people are moving into elliptic curve cryptography. So currently RSA encryption things are very popular, but as you can see, it is much less secure, right? The order of running time is 2 to the sub, it is sub exponential, 2 to the n, 2 to the n to the 1/3, right? Compared to that, for elliptic curves, the best known is around 2 to the n over 2, which is huge, right? So this is why elliptic curves groups can allow for more efficient cryptography. This is why elliptic curve groups can allow for more efficient cryptography. More cryptography. And which is why for number theory, the biggest employer of number theorists in US outside of universities is the NSA, because their cryptography, they're trying to get cryptographers because number theory is the backbone of elliptic curves and everything, and that is what cryptography is based on nowadays. Okay, so let's come back to cryptography. This was just giving you an idea of how big things are and how slow things are, and why it is important to look at elliptic curve groups, even though I am purposely skipping them. Okay. So far we were looking at private key cryptography, and it has its benefits, and the major use of it was it allows two users who share a secret key, who already share a secret key, to establish a secure channel. Establish a secure channel. Right? However, the need to share a key has several drawbacks. The need to share a key has several drawbacks. Right? You need to first share the key using a secure channel. Need to share a key. Using secure channel. I mean, some of these can be solved. Right? Some of these problems can be solved. The problem can be solved. The problem can be solved. Can be solved in some settings. Settings. Example, having a trusted courier, as in the Kremlin phone. Trusted courier. Physical proximity. Physical proximity. Shared beforehand and everything. Okay, so but these can be in other settings, this can be really expensive or difficult to solve. Can be expensive or difficult to solve in other settings. Okay. Now here's the worst problem. Okay. Imagine, so the key management problem. Imagine an organization. with 10 people, with n employees. Okay? Where each pair of employees might need to communicate securely. Where each pair of employees might need to communicate securely. Right? The solution using private cryptography, solution using private key cryptography is not really elegant, right? It says, well, you just want everyone to communicate. Well, give each one of them, each pair their own key. So each user shares a key with all other users, So that means each user is storing, managing n-1 secret keys. Each user must store, manage n-1 keys, which is not too bad, right? Each person is only saving n-1 keys, but that means the number of keys, number of storage, is number of is of the order of n squared overall. Okay, and that's a lot of data. Suppose when you have like 10,000 employees, n squared is suddenly a billion, right? 10,000 is 10 to the 5. You square that, that's suddenly a billion keys. That's huge, right? Also, it also creates problems for example, a new employee joins. Then you have to make them a key and distribute this key to every other employee. Say two users who have no prior relationship, who have no prior relationship, want to communicate securely. Right? If they have no prior communication, when would they have shared a key? When would they have shared a key? Right? And this is extremely frequent. Like, for example, every time you this happens all the time. For example, customer sending credit card data to a merchant, customer sending credit card data to a merchant who they have never purchased things from before, contacting a friend of friend, contacting someone new, contacting friend of friend, like let's say friend of friend, or emailing a colleague, emailing Emailing a new colleague. Hey, G. In all these circumstances, you might not have shared a key before, right? And so classical cryptography has no solutions to these problems. Classical cryptography offers no solutions. No solutions to these problems. And the funny thing is, this was the case till around 1976. Okay. In 1976, Whitfield Diffie and Martin Hellman published a paper, invited paper, on transactions on information transactions on information theory, called New Directions in Cryptography. And that is the first time they introduced how to do public key cryptography. Okay. So New Directions, public key cryptography. So what is the main idea? I don't expect you to go and read the paper. So I'll just tell you what the main idea is. Main ideas. Some problems exhibit asymmetry. Some problems exhibit asymmetry. Okay, which are easy to compute if you know what you're doing, but they're really hard to invert. For example, factoring, RSA, group exponentiation, enunciation, etc. There are a lot of these problems. Okay. So how do you do this? Now you use this asymmetry to enable two parties. Use this asymmetry to enable two parties to agree on a shared key, shared secret key, via public discussion. Okay, so I will shout out some details, okay, about about things, and you shout out some details back to me. I should be able to compute a key from that only you and I know. No one else should be able to figure it out, because for me it is easy to compute, but it is hard to invert from the given data. If you don't have some data, it should be really hard for you to break it. Key exchange. This is called the key exchange. Okay. So in terms of an image, key exchange. It should look like this. Okay. You have a user U1 who has some key in their mind, who has something that they are going to send to another user U2. And there's a whole lot of discussion here. Transcript. RCRIPT. Right? And this is visible to public. But security goal, even after observing the transcript, even after observing the transcript, the shared key should be indistinguishable from a uniform key. From a uniform key. Okay. Formally, fix a key exchange protocol pi and an attacker who is a passive eavesdropper A. Passive eavesdropper A. And you'll soon realize why you only need passive eavesdropper rather than anyone who can do any sorts of attacks, because we are sending data unencrypted initially. Everyone can see this data. There's no encryption going on. You need a key for encryption. We are trying to figure out how to set up a key, right? So passive eavesdropper is fine. Define the following experiment. Experiment. Key exchange of A with pi n. Honest parties run key. Honest parties run pi using security parameter n, resulting in a transcript which we are going to refer trans, and shared key k. Okay, great. Choose uniform bit B. Choose uniform bit B. If B is equal to 0, then set k is equal to k prime. If B is equal to 1, then choose a uniform k prime form k prime belonging to 0, 1 to the n. Okay. Give trans and k prime to A, which outputs a bit B prime, which outputs bit B prime, And we say the experiment evaluates to 1. A succeeds if B is equal to B prime. Right? Which is to say, the adversary could guess if this is a uniform key or not. If it's actually the key or some uniform bit. So, what is my security question? What is the security goal? Security. A key exchange protocol Pi is secure. Key exchange protocol Pi is secure against passive eavesdropper if for PEA. What was the thing we were using? PES? I don't remember. Passive eavesdropper. If for all probabilistic polynomial time, if for all PPT algorithms A, it holds that. The probability that KE of A comma pi of n is equal to 1 is smaller than or equal to 1/2 plus negligible function of n. Right? Epsilon of n, where it is okay. Note, what we are asking is something stronger than just you cannot compute the key. Being unable to compute the key is not a strong enough guarantee. Key given the transcript, given transcript is not a strong enough guarantee. What we're asking is it should be we're basically saying even if I show you the key, you should not be able to say, oh yes, this is the key. Of course it makes sense, right? It should be completely indistinguishable. So indistinguishability is indistinguishability of the shared key from uniform is a much stronger guarantee. Okay. And in fact, it is necessary if the shared key will be subsequently used for private key. Because what is the plan? You want to set up something so that you can exchange keys, and then now that you both have a shared secret key, you can be like, oh, now we have each other's keys, now let us talk in secret using previous definitions, previous notions of private key cryptography, because now you have exchanged keys. Even though you did it in front of everyone, no one came to know. So you have seen some way of doing this before. It might not be obvious still. So let us look at the Diffie-Hellman key exchange. Diffie-Hellman key exchange. Okay. How does this work? You have a user U1. And another user U2. Okay. The user U1 does obtains G, Q, and G from given parameter and giving the key the group generating algorithm 1 to the n, right? So it spits out security parameter. Oh, sorry, not you feed it a security parameter, spits out the group info and some size of the group and the generator of the group. You take a random element x from G. You take h1 is equal to G to the x. Okay? And you share this info around. You share G, Q, G, H1. Other person gets a random Y in ZQ. They have seen what the size Q is. So they take a uniform Y in ZQ. Okay? And they take H2 is equal to G to the Y. They send H2. So what is the key? U1 calculates key K1 by H2 to the power X. U2 calculates key K2 by H1 to the power Y. So, in practice, generally in real life, what is happening is you have U1, you have U2, and G, Q, G is public knowledge. Okay, everyone knows these. So let me just maybe draw my figures slightly. Practice G, Q, G is out there in public. Okay. The user U1 sends just H2. That's right, H1. User U2 sends H2. How are they doing? Again, take X and Q. ZQ, H1 is equal to G to the X. Y in ZQ. H2 is equal to G to the Y. And then we calculate the keys again by K1 is equal to H2 to the X. K2 is equal to H1 to the Y. And what makes it hard is that even though you're sending H1 and H2, even with G known to everyone, finding X1 X and Y is hard. Okay, so recall Diffie-Hellman problem. Hellman decisional Diffie-Hellman problem. What did it say? Given g to the x, g to the y, distinguish g to the xy from a uniform group, uniform form group element. That is what the Diffie-Hellman problem says. Now, in this case for security, what is happening? Eavesdropper, EAVES, dropper A sees G, Q, G, and G to the X and G to the Y. He does not see what X and Y are, just E to the X and E to the Y. Now the shared key becomes is G to the XY. For the adversary, this is exactly computing K. From the transcript. Is exactly the computational Diffie-Hellman problem. Right? Whereas the definition of security that we asked for, which said distinguish K from a uniform group element, uniform group element is exactly the decisional Diffie-Hellman problem. Decisional Diffie-Hellman problem. Right? As a result, we get that if the DDH problem is hard relative to G, then this is a secure key exchange protocol. Then this is a secure key exchange protocol. Okay. I'm going to stop here for today. Okay. I will go into slightly more details next time. And then move on to chapter 11. Okay. So this is giving us an intro into the world of public key cryptography. Okay.